In this presentation, we continue our discussion of thin lenses, but we will look at this more formally by applying the thin lens formula. So we looked at thin lenses from the perspective of using geometric optics, where we look at rays of light that leave the top of an object and pass through the lens and form an image. But it turns out that we can't always draw pictures, and so we'd like to have a more formal way of actually calculating perhaps where an image will be formed when an object is placed in front of a particular lens. So in our picture here, we have a thin lens. This happens to be a converging lens. We have the principal axis, and then we have our object that's located over here on the left, and our object has some height, which is labeled as h with a subscript of O for the object. We have the rays of light that form the image. We've got a ray of light coming in parallel, passing through the focal point, a ray of light passing through the focal point, coming parallel, and then the ray of light going directly through the center of the lens, and they all meet where the image is formed. And we see that our image in this particular case is inverted, and it has a particular height associated with it, and that's labeled as h with a subscript of I for the image. The other important labels in our figure is the focal length, which is the distance from the center of the lens out to the focal point, and we see that we can measure that on either side of the lens with respect to the center of the lens and the focal point on either side. And then we have the distance from the center of the lens out to where the object is located, and that is called our object distance, so the distance from our object to the lens, and we label that as a P. And then we also have the image distance, which is the distance from the center of the lens out to where the image is located, and we label that as a Q. So the thin lens formula provides a way of comparing where the object is located to where the image is located based on what the focal length of the lens is. And it turns out that 1 over the object distance plus 1 over the image distance will always be equal to 1 over the focal length. Additionally, we can talk about the magnification of the image compared to the object. And the magnification is going to tell us a great deal of information about the image that's formed. So it'll tell us whether the image is upright or inverted. It will tell us whether the image is larger or smaller than the object. So in general, we define the magnification as the ratio of the height of the image to the height of the object. And the height here is represented in terms of a length, and it can be any units of length: meters over meters, centimeters over centimeters. So the units for the magnification is unitless. But it is important also to take into account whether the image is upright or inverted. So if an image is upright or an object is upright, it would have a positive height, and if it's inverted, it would have a negative height. The other way that we can define the magnification is it turns out that the magnification is equal to the ratio of the image distance to the object distance, with an overall minus sign in the front. So these formulas for the magnification as well as the formula for the thin lens are derived by using the geometry of the geometric optics picture. And we're not going to go through all of that geometry, but we're going to use the thin formula and we're going to use the magnification formula. So when the magnification and the image height are positive, that means that the image is upright. Any image that's upright will always be virtual, and it will always be on the same side of the lens as the object is. When the magnification and the image height are negative, the image is going to be inverted. It will always be real if it's inverted, and it will always be on the side of the lens opposite to the object. So the positive and negative sign of the magnification is going to tell us a lot about the type of image that we have, whether it will be upright and virtual or inverted and real. The magnitude of the magnification, which is just the number that we get without the plus or the minus sign, tells us something about whether the image is larger than the object or smaller than the object. If the magnitude of the magnification, the number itself, is greater than 1, that means that the image is larger than the object. And if the magnification is less than 1, that means that the image is smaller than the object. And we're going to look at some examples a little bit later. So we can put all this together on a sort of a chart that lets us decide the sign conventions by using the thin lens formula and the magnification. So in terms of focal length, you will have positive focal length if it's a converging lens and negative focal length if it's a diverging lens. In terms of the image location, if the image is located on the opposite side of the lens as the object, that means it's real and inverted, and it will be positive. If it's located on the same side of the lens as the object, that means it's virtual and upright. So an image, so it doesn't have to be a diverging lens to have an image that's on the same side of the lens as the object, because we saw that converging lenses can also have that. So these are really separate things. This is just telling you positive when the image is inverted and real and on the opposite side of the lens, and negative when it's on the same side of the lens and it's virtual and upright. We could also talk about the magnification. If the magnification is positive, that means the image is upright, and if it's upright, it has to be virtual. And if the magnification is negative, it means that it's going to be inverted and real. We could also look at the magnification and the magnitude, and we just said that if the number itself for the magnification is greater than 1, then the image is larger than the object, and if it's less than 1, the image is going to be smaller than the object.